All right, so welcome to another fun-filled day of calculus. Our plan today is to keep going with derivatives and talk about some more ways of differentiating and all that. Specifically, we're going to look at inverse functions, how you can actually take a derivative of an inverse without finding the inverse. It's kind of nice. And then we'll use that to develop some more rules for other kinds of functions. So that's kind of our plan, is just to sort of keep going with the idea of differentiation. Before we get there, though, any questions about the homework or anything else?
I had a question. I forgot what problem it was, but it was on the chain rules one. I think the question was 5 times negative 6x to the 6th plus 8x to the 5th to the 8, and then the whole thing in parentheses to the 18th. And it said do not round. I sent you a comment really late last night, so I really apologize because I know you're sick. But then I put my answer as negative 540 x to the 6th plus 720 x to the 5th. I wasn't sure if you wanted me to multiply by the 90 at the last step.
Okay, so I'm having a hard time tracking that, what that problem was. So
I think it was like number 4 or number 5 on the chain rule.
So what I'm going to do is I'm going to go find it real fast.
Sorry.
No, it's quite all right. It just I'm a real visual guy.
You have to see it.
My auditory, yeah. So like when people will read something like that to me,
it's like 5 parentheses and then to the 18th.
All right, well, let me just see if I can find it here. You said you thought it was around like number 4 or 5, something like that?
Yeah.
Okay, so I see one.
It won't be the same question, but it'll be similar. So
yeah. Well, let me just share mine real quick, and because I think I found the one that you're talking about. So let's see.
Yeah, I'm not sure how the system wanted me to write my answer when it said do not expand.
Okay.
And I was like, I did not expand.
So I think what they're saying when they say do not expand out your answer means when you've got that binomial raised to a power, like right now it's raised to the 12th, it's saying don't go ahead and multiply that out. Don't FOIL it out. Don't do all that.
Okay.
So here's how I would approach this problem. Let me just really quickly write it down here. Okay, let me share my whiteboard.
Yeah, the first thing I did was let the inside be u.
Okay.
I'm not sure if I already screwed up on that step, but if I did, that's okay.
Well, let's just talk about this. If we're going to differentiate, let's just kind of follow this step by step. So first, we've got a 5 that's a multiple, right? It's a constant multiple. So I know that that's just going to come along down, right? Constant multiples just go for it, right? Okay. So then I've got this thing being raised to the 12th. So you called it u using the kind of the power rule, general power rule idea. I'm just going to think of it as this is the inner function raised to the 12th. So I'm going to differentiate that next. So I've got something to the 12th. So the derivative of that is going to be 12 times that something to the 11th. Right? So that's the general power rule. This exponent, right, comes out front. And then we subtract 1 to get to the 11th. So now comes the chain rule. And the chain rule now says we need to differentiate the inner function. So I'm going to put another parenthesis here. So we've got negative 3, it's a constant multiple. The x to the 5th is going to give us a 5x to the 4th.
Can I just write negative 15x to the 4th?
Sure.
Okay.
That's what I'm going to do on my next step. I just wanted to show all the steps for folks that are still a little bit uncomfortable with it. So we have minus 2, again, constant multiple, and then x to the 10th. That one becomes 10x to the 9th.
Thank you.
So I would do one more step here. 5 times 12, I would go ahead and combine those. And then I'd leave this as minus 3x to the 5th minus 2x to the 10th to the 11th power times minus 15x to the 4th minus 20x to the 9th. So this is what I would try to put into the computer. So to kind of get back to your original question, Susanna, like if it's just numbers that are being multiplied, I always multiply those together. And that's a pretty common thing to do.
Because from this step, I did the extra step where I distributed the 60. Well, my number was 90, but on this one it would be 60. So I did, so it would have been like 180, negative 180 x to the 5th minus 120 x to the 10th, and then the whole thing to the 11.
Okay, so if you do that distribution, then you unfortunately are not correct anymore.
Okay.
Because this is to the 11th, right?
Yeah.
If you distribute that 60 through, so if you were to write like minus 180 x to the 5th minus 120 x to the 10th to the 11th, what you really did, let me just factor it out here. Oops. It's supposed to be a minus 3. Hold on one second. Right, by the rules of exponents, this is saying this is 60 to the 11th times minus 3x, right? And so what you actually did was you changed it significantly. You actually multiplied by 60 to the 10th.
So I should have just left it in like the step before. Yeah. Okay, that makes sense.
Now, if you wanted to distribute it, like you legit want to get that 60 in.
Move the exponent first.
Well, you can't really do the exponent.
Oh.
Like move the exponent because the exponent's where it is. But what you could have done is you could have actually taken that 60 and distributed it into the other one. That would have been okay because this is just to the first. And since this is all multiplication, you can do multiplication in any order you want, right? So I could take the first thing times the last thing. I don't have to do them in order necessarily. But I would highly recommend that you not do that. Let me just give you a little tip for where we're going. One of the biggest things we're going to do with derivatives is we're going to look and see where they're equal to 0. That's going to be one of our goals. And it's a lot easier to figure out where things are equal to 0 if they're already factored, right? Because you can just set the factors equal to 0. And so in general, you want to fight the urge to multiply stuff out in the derivative.
Okay.
Sometimes you want to do that, but in many circumstances, that's going against the direction of where you want to be.
Okay. Thank you.
Yeah, you're welcome.
I just didn't think the answer should be that long. I think that's what tripped me up.
I know you're looking for a nice thing like 4x, right, or something like that, and no.
I was thinking like a 2, like at most. What is it called? A binomial?
Yeah. Well, you're going to see as we do more and more of this differentiation that derivatives can be really big and gnarly. And it really depends what the original function looked like. There is a lot of simplifying that could be done, right? Like obviously we could have started by distributing this out and gotten just a polynomial. I mean, it would have been crazy. It would have been, the biggest degree would have been x to the 22nd, or no, x to the 120th.
Oh wait, I'm looking at my work again. I actually did what you told me to do, where I got the number, the parentheses that was to the first, and then I multiplied it with the
second one.
With the constant in the front.
Oh, okay.
Yeah, I did that, and then I think the system still counted me wrong. So.
Well, if
but
you
that's
want,
okay.
I can go look at it and if what you have is correct, like is the same thing, I'll go ahead and give you the point. You know what I mean? Like if
Mm-hmm.
the only reason it didn't give you the points is because you took that 60 and actually passed it through,
Uh-huh.
then that's silly. I'll give you that point. So
Okay.
I'll go and look at that. Will you send me, you said you already sent me a message?
Yeah, I believe I did.
Okay, then that should be enough to remind me to go and look at it.
All right. Thank you.
You're welcome. Any other questions from the homework?
I have one.
Okay,
Could you do number 5 from the chain rule?
sure. So same set. Let's go take a look at it. All right, so is that looking like what you wanted to see? I mean, yours is probably just slightly different, but
Yeah.
okay. So this is another one where it just says use the chain rule to find the derivative of this. First of all, before we get to the rest of it, how do you know you need to use chain rule? Like, I mean, I know they told us, but how would we have known even if they hadn't told us? Well,
The square root.
Yeah, because there's stuff inside that square root, right? Real quick, why I asked that question is think about like on an exam or a quiz. I'm not going to say use the chain rule to find the derivative of this. I'm just going to say find the derivative of this function. And so we need to be able to look at it and recognize which rule, you know, even though we're like, we know it's going to be chain rule because we're in the chain rule section. But what tells you that you need chain rule is you've got stuff inside of another thing, right? Anytime you've got, you know, composition stuff inside of other things, that's when you use chain rule. All right, so we're going to differentiate this thing, and then it just said give your answer without fractional or negative exponents. So if they're fractional exponents, we'll turn them into roots. If they're negative exponents, we'll move them to the denominator, right? We'll just use those rules. All right, so let's go back to the whiteboard then. Let me go ahead and clear all this other stuff. All right, so here was our function. We were told f of x is equal to 10 times the square root of 6x to the 4th plus 7x to the 8th. All right, so let's do substitution. Let's do the chain rule. And this time, let's use the U substitution idea. Let's build the chain this time just for some practice with that. So we'll let U equal the stuff inside. So this then looks like y equals 10 square roots of U. And this we're going to be able to differentiate if we recognize that that square root is just a 1/2 power. So if you're still kind of unfamiliar with that, it's going to really, really, really become second nature for you because we do this all the time in calculus. It's way easier to see these things as exponents or use them when they're exponents. All right, so there's our y. We can easily differentiate that. If we look at u, u is also easily differentiable. So now we're ready to build our chain. So dy dx, it's going to equal, the first link in the chain is going to be dy du. I'm starting with y because that was what's on top. But this is dy du because our function is now in terms of u. All right, so the next link, excuse me, is going to be a du dx, right? It needs to be a du because that's going to be the next variable here. And then it's a derivative with respect to x because that's what u is written in terms of. So this one's small, only has 2 pieces, but let's go ahead and get their derivative so we can put them together. All right, so let's start with du dx, just because I'm here. Du dx, power rule. So x to the fourth, we bring that 4 out front as a multiple, so that's going to get us 24, and then x to the third. The next piece, that 8 comes out front as multiple. 8 times 7 is 56. And then we decrease the exponent by 1. So du dx is 24 x cubed plus 56 x to the 7. All right, now we also need dy du. So let's get that one over here. Again, bring that power out front as a multiplier. So 1/2 times 10 is 5. And then we decrease this exponent by 1. So 1/2 minus 1 is minus 1/2. But they told us not to have negative exponents. So let's think of this as 5 over u to the 1/2. Remember, negative exponents just drop us to the bottom. Then we can make them positive. But they also said no fractional exponents. So let's turn that back into a root. So that's 5 over the square root of u. All right, so we've got dy du, we've got du dx. We'll just multiply those together. So we got 5 over the square root of u times 24x cubed plus 56x to the 7th. But there's one more thing we have to do with this. What do we still have to do with this answer? Because if you try to put this in, it'll definitely give you the red X of shame. Well, okay, so Lee, you just said put it all over square root of u. That's actually not the actual issue, but Bailey just got it. We actually have to plug in for u, because if you look, remember originally our derivative is with respect to x, right? Or if you go back to the original function, our variable is x. We need only x's here, which means we got to get rid of this u. But we already know what u is. We did that substitution earlier. So we just got to go and fire that sucker in here. So we need to replace the u. But I am going to do exactly what Aaliyah said anyway. I'm going to make it all over the square root. But it's going to be the square root of 6x to the 4th plus 7x to the 8th. So there's the derivative of f. So if we want, we can write it in the Newton notation. And this is another one, if you wanted to, you could pass that 5 through. I wouldn't recommend it. I would just leave it like this. I doubt that the computer is going to penalize you if you put it in like this. If it does, that's another one of those things where if you feel like you did it right, but just something's up, send me a message and I'll look at it. And if you actually did give an equivalent form, I will give you the points. If not, I'll explain what you did. So if you do this, if you do the whole use substitution thing, which is totally cool, I do it all the time. If you do that, just make sure that you plug back in for all those letters. You got to get back to the original variable. All right, so I think, was this Tim, did you ask me about this one?
Yeah.
Yeah, is that good? Does that make sense?
Yeah, that makes sense.
All right, awesome. Okay, anything else? All right, well then we will switch screens here. Give me just 1 second and I will meet you up at the whiteboard. All right, so today's plan, like I said, we're going to keep going with derivatives, but specifically, we're going to start talking about the derivative of the inverse. All right. And like I mentioned before, and I don't know if you caught this, but we're going to actually develop a way to find the derivative of an inverse function without finding the equation of the inverse function, which is going to be kind of handy. Because obviously, if we can find the equation of the inverse function, we're good to go, right? We just find the inverse, we differentiate it, and we're good. But it'll be nice to have this so that we don't actually have to do the algebra. But before we get to the derivatives of inverses, let's remind ourselves a little bit about how inverses work. Okay, so if we've got f of x, its inverse is f to the minus 1 of x. Right? This is the notation we use. And I do want to warn you, because this is going to happen, you're going to mix this up with the derivative. It's a very similar notation, but it's different, right? So that's the inverse, where the derivative is just f prime. So watch out for that. Just watch for that. It's quite possible that you'll fall into that. We just got to be really careful, because the notation is very specific, right? So f inverse is with that little minus 1. But remember what inverses do, right? Inverses, these are basically they undo each other. They go the opposite direction, right? And so some things that are important to remember, that the y's and the x's swap, right? The roles of y and x swap with inverse functions. If we draw their graphs, the points, you literally switch the coordinates, swap the coordinates, and that's the point on the inverse. When we solve for the inverse, remember what we do, we change y's to x's, x's to y's. The domain of one is the range of the other. That's the role of x and y swap. So this is a really important thing to remember, that the roles of x and y alternate. And then the other thing that's really important is this undoing each other thing. And that is that if you compose inverses and you compose them in either order, either way, you get x. So these are the two really important things I want you to remember. The first one, there's a lot in there, right? Like I mentioned, things like the domain and the range swap. That's a subset of this. It's important to remember. The graphs are symmetric. They actually are mirror images of each other over the line y equal x, right? So those are kind of the more important things that are within that x and y swap. All right, so this is basically our goal today, is to take inverse functions and see if we can figure out how their derivatives are related to each other. And the derivatives definitely are related to each other. Since inverse functions are related, we should expect that their derivatives are related, but we're going to see exactly what that relationship is. Okay, so remember these facts. We're going to use those a little bit today. All right, now, what we're going to do is I have to introduce you to something that we do with the derivative. Like, you're used to now the derivative as a function, right? It's telling us about a specific function that's ready to change the slopes of tangent lines, right? I mean, that's what the derivative is. But the derivative is also an operation, okay? It's something that you can do. You can differentiate something, just like you can multiply something, or you can add, right? So this is an operation. And so something that we often do is, given an equation, we will differentiate both sides. All right, so let me just kind of write this up here because it's kind of a big important thing, is that given an equation, you can differentiate both sides and maintain equality. All right, so basically, think about what an equation says. Equation says we've got two things that are equal, they're identical. And what I just wrote there says that, well, if I've got two things that are the same, if I differentiate them, their derivatives are going to be the same. And that should make total sense, right? Think about what derivatives are, their rate of change, or slopes of the tangent lines, or whatever. Well, if two things are equal, if they have the same graphs, they should have the same rates of change, which means they should have the same derivatives. So, like so many other things, given an equation, we can actually apply a derivative to both sides and still have an equation. Just like you can square both sides and still have truth. You can take a log of both sides, still have truth, right? You can add 5 to both sides, still have truth. We can differentiate both sides and still have truth. Okay, so we're going to make use of this today. We're going to make use of this fact today a lot. And in fact, the next couple of sections in this chapter, I'll do this, take derivatives of both sides. So this is something that you're going to get used to. And it'll make sense, or the process will make sense as we go along. All right, now the reason I brought that up is because I want to look at this second fact about derivatives. You notice that I do have an equation. I mean, I've got like 3 pieces of this equation. Well, I'm just going to strip this apart, and I'm going to look specifically at the first one that says, if I look at f of f inverse of x, that equals x. Okay, so that was this little first piece. But again, this is just the whole point of inverses, is that they satisfy that. So here we go. Let's differentiate both sides. So the way that I'm going to represent that we're going to use the derivative as an operation is I'm going to put a d dx on each side. So remember that Leibniz notation version. I don't have anything on top, it just says d. So the way to read this is I'm saying I'm going to differentiate with respect to x. And so the golden rule equations, right? What you do to one side, you got to do to the other. Well, I'm doing that here. Differentiating both sides with respect to x. Okay, so we're just going to differentiate both sides of these things. The right-hand side is pretty easy to see what happens. Because what do you get when you differentiate x? What's the derivative of x? All right, good. Bailey just put in the chat box, and oh, there comes some more. It's just 1. Okay, so on the right-hand side here, this is just going to equal 1. Cool, nice and easy. All right, well now when we go on to the left side, we're going to differentiate, but notice that this is going to require chain rule. And it requires chain rule because we're doing composition. We've got one function going into the other. So think about the chain rule. The chain rule says we need to differentiate the outside function. Okay, so we're going to differentiate f. I'm going to leave it just as f prime because I don't know what f is yet. I want to leave it generic. But I'm going to differentiate f, and then I need to evaluate that at f inverse. But then the chain rule says the next step is to differentiate what's inside. Okay, well, so that's going to be I'm just going to write this as the derivative of f prime, or sorry, f inverse. See that thing I warned you about? You're going to get them mixed up, inverses and derivatives. I even just said it right there. I called it f prime. It's really easy to make that mistake. All right, so this left-hand side, this is just chain rule. I know it doesn't really look like it. I know it doesn't look like it. But if you go back to how we defined chain rule, remember the very first time when we did chain rule, we did f of g of x. Well, if I were to call this guy g of x, you would totally see it. It's f prime of g times g prime, right? So f prime of g times g prime, that was chain rule. Well, that's exactly what we've got going on. Okay, so it's just chain rule. However, notice that we now have the derivative of the inverse. And I can take this equation and I can literally solve it for the derivative of the inverse. So we're going to get that the derivative of an inverse function it's actually equal to 1 over the derivative of the original function evaluated at the inverse.
I'm a little bit confused. Doesn't the one on the left also mean the derivative of the inverse?
This is the derivative of the original function evaluated at the inverse, where we're plugging the inverse in.
Okay.
So that's why I'm using a different notation, because these parentheses are literally saying composition, as opposed to these brackets are saying take the derivative of what's inside. So I know that the notation gets a little bit funky here, but this is the derivative of the outside function evaluated at the inner function. But that was a good question, Leanne. Okay, now, believe it or not, we're done. Let's go ahead and put a box around this. Right, because we know that as soon as we put the box around it, that signifies that we finished doing whatever we were doing. But this is the important statement right here. Let's talk about it. Let's actually see what it means and what it's doing. Okay, so the left-hand side, of course, is the derivative of an inverse. All right. But what we're told, or what we see from this, is that it's actually just the reciprocal of the derivative of the original function. It's 1 over that. So like if we had originally had a function whose derivative was 1/4, the inverse's derivative is going to equal 4. If the original one had a derivative of 2, the second one, the inverse is going to have a derivative of 1/2, and so on. So basically what this is saying is that to get the derivative of the inverse, all you need to do is get the derivative of the original function and flip it over. That's it. All right, so it turns out that the derivative of an inverse is actually the reciprocal of the original function's derivative. But there is a slight little catch that we need to talk about. It's this f prime of f inverse of x. But let me do this. Let's actually draw a graph of a function that we know that has an inverse. We'll also draw the graph of its inverse, and we'll see how this is playing out. All right, how we're getting slopes that are reciprocals of each other. And so the function I want to look at is the square root of x, because we know that one pretty well, and it's also really easy to draw the graph of it. And it's also really easy to find the inverse. So let's think about f of x equals the square root of x. So I'm going to draw the graph down here. And I'll try to draw it fairly well. So I'll even put on some tick marks here and everything. All right, so the square root of x looks something like, goes through 0, 0, 1, 1, 4, 2, looks something like that. Okay, so there's the square root of x. Specifically, let's look at the slope of the tangent line out here at 4, 2. Okay, so this is the point 4, 2. Let's real quick find the derivative and see what the slope is at that point. So this is x to the 1/2. So if I differentiate, I get 1/2 x to the minus 1/2, which is the same as 1 over 2 root x. So at 4, I get 1/4. So the slope of the line, the slope of this tangent line at that point is 1/4. And you can see that on the graph. It's positive, but it's not very big. I'm going up 1 every time I go over 4. Okay, so this has nothing to do with inverses, right? It's just that function. But now let's look at its inverse. So can anyone tell me what the inverse of the square root of x is? Does anybody know that one off the top of their head?
Is it x squared?
It is x squared, yeah. Think about it. How do you undo a square root? You square it. How do you undo a square? You take the square root, right? So that's just how inverses work. If you don't see that, you can actually solve for it. If we just do the whole y equals square root of x, swap x's and y's, solve for the new y by squaring both sides, you get y equals x squared. So that is the inverse for this one. So if f is square root of x, then f inverse is x squared. Okay, so let me draw in x squared. So again, I'll try to do this fairly well. 1, 1, 2, 4, and so on. We'll call that good enough. So there is the graph of x squared. You can see the symmetry, right? Think about the line y equals x. That's this line right there. And the blue and the green are mirror images over that. Okay, so we know that happens with inverses. And we also know that the points, the roles of the points, the x's and the y's swap. So we had the point 4, 2 on the graph of f, which means that there's a point 2, 4 on the graph of f inverse. Yeah, 2 squared is equal to 4. And let's look at the slope of the tangent line at that point. Okay, so here's a different red line. This is the tangent line at that point. Well, if we were to look at this function, y equals x squared, and we were to differentiate it, we'd see that y prime is equal to 2x, which when x is equal to 2, gives us 4. And so I want you to first just notice that these two slopes are reciprocals of each other. That's what this this statement in the blue box is saying, is that the derivative is related to the original function. It's just flipped over. And this just comes from the fact that y's and x's swap when we're dealing with inverses. So since the role of x and y swap, dy dx, dx dy, they're just reciprocal. So hopefully this example shows you why this is true, or, well, helps justify this. The why this is true is because the math says so. But this example should help it feel right, that it actually works this way. Okay, but this also brings up that, remember how I told you, well, there's one kind of little issue that we need to deal with. And I want you to think about this. What did we plug in to get the derivative for the first one? What number did we actually plug in? I know you can all see it. You probably just are that way today. But we plugged in 4, right? Did we plug in 4 into the other function? No. We plugged in 2. Right? So we plugged in different values. But the 4 and the 2 were related to each other. Right? If we go back to this original thing, right? The 2 was what came out when we plugged in 4. So it wasn't random. It wasn't that I just randomly chose to plug in 2. No, I plugged in 2 because it was the number that was associated with 4 through this function. Well, that's what this says. That's what this is saying. When we say f inverse of x, that really is saying, well, plug in the x value that came from the y, or vice versa, right? So like in the context of what we did, right? Context of what we did, we plugged in 4 because 4 came from 2 squared. That's what this is saying. So when we do this, when we just invert it, we are going to have to remember, though, that we're plugging in what came out of the inverse function, not what's going into the inverse function, right? We plugged in the 2 because that's what came out of this. We didn't plug in 4, right? With this other function, we didn't plug in 4. We plugged in 2 because that's what came out. That by far is going to be where this causes you trouble. Just that. Again, this has nothing to do with you guys personally, right? Because I don't know your all's calculus skills, you're brand new to this, but I've taught calculus a lot over the decades. Routinely, that's where students run into problems. Okay, so we just got to be really, really careful with that. We got to watch for that. But once we get past that, once we get to the point where we can deal with that, this is a lot faster than actually trying to solve for the other function and then take its derivative and so on. So let me show you another example. Let's take a function that we've not done before and one that has an inverse. And we'll actually see how we can apply this right here to get the derivative of the inverse without actually finding its equation.
Just quickly, you were saying that you plugged in 4 to f of x, not f prime of x, right? To get at what you were going to plug into f inverse?
Correct.
Okay.
Yeah, so notice that, like, so I plugged in 4 in f prime, so that was going into the original function f, where the inverse I was plugging in 2. I didn't write it over here, but this would be like f inverse of 2. So we're plugging in the 4 and the 2, we're plugging in different numbers into the different functions because 4 and 2 are that pair, the corresponding pair for either one of those points. hopefully when I do this next example, you'll totally see how this goes. All right, so here is a function that is one-to-one. All right, so we've got f of x equals x cubed plus 3. But what I want to find the derivative of f inverse of 2. Okay, so I gave you a function. I don't care about its derivative. I'm concerned with the derivative of the inverse. And I specifically want to know what's the derivative of the inverse at 2. Okay, so let's just think about what we could do. We could find the equation for f inverse, right? Do the whole y equals x cubed plus 3, swap, solve. Then I could differentiate that. And then I could plug in 2. Right, so that's one of the options. And in fact, let's do that. Let's just slug this one out so you can see.
Would that be your only option if you weren't solving at a specific point?
No. Well, yes. Yes and no. We're going to go with yes. We're going to go with yes. There are some workarounds, but I don't want to go into that. But yes, if it was not at a specific point, we'd have to plug in the inverse function. So let's find it real quick. So we've got y equals x cubed plus 3. So we'll swap and solve. So we change the x's and y's. We now solve for the new y. So we get y is equal to the cube root of x minus 3. So this is our inverse. Okay, so now let's differentiate it. So think of this as a 1/3 power. That will help us here. And so now to differentiate, we need the chain rule. So we bring the 1/3 out front. We decrease that exponent by 1. So 1/3 minus 1 is minus 2/3. And then we have to multiply by the derivative of what's inside. But x minus 3, its derivative is just 1. So this is 1 over 3 times x minus 3 to the positive 2/3. So there's the derivative. And now we'd evaluate this at 2. So if we're going to do the derivative of f inverse at 2, we'll plug in 2. So we get 1 over 3 times 2 minus 3 to the 2/3. 2 minus 3 is minus 1. Minus 1 squared is 1. Cube root of 1 is 1. Times 3 is 3. And we end up with 1/3. So this was just slamming through, right? We want the derivative of the inverse. Okay, find the inverse, do the derivative stuff, plug in the number. We got 1/3. So that is always an option. It does, however, require that you are able to find an equation for the inverse, which isn't always the case, right? But we got to be able to find the derivative. All right, well, there you go. Now, instead, let's think about this box statement that says the derivative of the inverse is going to be the same as 1 over the derivative of the other function, the original function. We just have to evaluate that other function at a different point. Okay, so there are two things we got to do. One is we have to differentiate f. But the other is to figure out what do we plug in to actually get 2. Okay, because we need to know that other part of the point, right? Remember that when we did this before, like with that point 4, 2, in one case it was 4, 2, the other one it was 2, 4. So we need to find that pairing because we need to use the other number when we're dealing with the inverse. Okay, so let's actually tackle this into 2 steps. So the first thing I'm going to do is I'm going to take my original function, x cubed plus 3, and I'm going to set it equal to 2. So this is that find the other part of the point. What number goes along with 2? I'm using my original function because that's all I know. I don't know the inverse. I know my original function. So I'm basically looking at, all right, if I'm putting 2 into the inverse, that 2 is coming out of the original function. X's and Y swap. So what number do I plug in to get out 2? Well, if I solve this real quick, subtracting 3 from both sides, I get x cubed equals minus 1. And then I take a cube root, and I get x equals minus 1. So those are the 2 points that go together, minus 1 and 3. Okay, so the first step. Now we're going to use that fact that the slopes are reciprocal. So what I'm going to find then is that the derivative of the inverse at 2, that's going to equal 1 over the derivative of my original function at minus 1. So notice what I did. I just put in that number we just found, because I have to evaluate it at the other point, at the flipped point. So if I'm plugging 2 into the inverse, I have to be plugging minus 1 into the original function. So that bit that I had boxed here, that I just erased, this is what it looks like in our case. It's going to be 1 over f prime, but evaluated at negative 1, the corresponding value that goes with 2. Okay, so now check this out. Let's get the derivative of f. So f prime, go to the original function. X cubed plus 3, its derivative is 3x squared. Power rule on x cubed, and then the plus 3 goes away, right? So if I come back over here, this is going to be 1 over 3x squared, but with minus 1 in there as x. Okay, well, negative 1 squared is 1. 3 times 1 is 1. And notice that we got a value of 1/3, which is exactly what we found when we did it the just slug it out and push through it way. So we got the same value, which is good because that definitely helps support the fact that this theorem, this formula works. And it does. I mean, it has to work. But notice how much easier this way was. Way easier. The derivative was simple, right? Going from x cubed plus 3 to 3x squared was fast. And all we had to do was figure out what that other number was that we could plug in. So that's the general process when we're in this sort of a situation, is we don't actually have to find the formula for the inverse. I didn't even touch it this way. All I had to do was find the other value that corresponded with the 2 that we were plugging in. Okay, so questions on that one. How's that looking? Did it make a little more sense now that you saw an example? I'm going to assume that silence means, yeah, we're good. Okay, so let's do another one. Let's do another function that has an inverse. But this time it's going to be one that maybe we can't actually solve for the other point. All right, so let's look at this guy. Let's say this is our function. F of x equals x to the fifth plus 3x cubed minus 4x minus 8. All right, and I want to find F inverse of minus 8. Or sorry, not F inverse, the derivative of F inverse of minus 8. Okay, so exact same idea. We want to find the derivative of the inverse of this thing, evaluated at minus 8. All right, now think about what our options were. The first option was to go ahead and find the inverse function and then differentiate it, right? And then plug in minus 8. Now I want you to consider this. I'm going to write something down on the board. We're not going to go this way. But again, think about the whole swap and solve. So we have y equals x to the fifth plus 3x cubed minus 4x minus 8. We swap the coordinates here. So x's become y's and y's become x's. And the next step would be to solve this for y. So how do you guys feel about that? You want to do it? Please say no. I mean, where would you even start with that? Trying to solve this thing for y? Are you kidding me? Thanks, Mariola, by the way, for just saying no. Yeah, like trying to solve this for y isn't going to happen. So trying to find the inverse of this function, it's not viable. It's not really an option. So instead, let's go to the, well, what if we use that formula we just developed where we can get the reciprocal of the other function, the original function? Okay, so we have to do two things, right? The first is we need to figure out what x value can we plug in to get negative 8. All right, so can we do that? Yeah, sure. We can solve this thing, right? We can solve this. And I'm just going to tell you, just to help you out here, is that you get a solution of x equals 1. Right? If you plug in 1 to the fifth is 1. 3 times 1 cubed is 3. 1 plus 3 minus 4 is equal to 0. So we get negative 8. Turns out there's more than one x that does this. What I gave you isn't exactly invertible. It's not a one-to-one function, but we're going to pretend that it is. Okay. So x equals 1 is such that when we plug it in, we get minus 8. All right, so this is huge because now if we want to get this derivative, we just have to find the derivative of f. All right, so let's write that again. So if f of x is x to the fifth plus 3x cubed minus 4x minus 8, its derivative is going to be 5x to the fourth plus 9x squared minus 4. So let's plug in 1. So we get 5 plus 9 minus 4, which is 10. All right, well, that tells me that the derivative of the inverse of this thing at minus 8 is 1/10. Boom, done. We didn't have to bother and solve that thing's derivative. We didn't, right? What we could do instead of finding the inverse is this little trick. So I want you to notice what we did, right? Not once did I actually touch the inverse function. Everything was with f, and I did 2 things with it. 1, I figured out where that function equaled the number we were plugging into the inverse. Okay, so do that. And then I found the derivative at that point for my original function. Okay, and then as soon as we're done with that, okay, just take the reciprocal. So think of this as, like, in reality, what this is the workaround for finding the inverse. All right, so Aaron, so we wouldn't know that x is 1 just by looking at the equation, though. Okay, you're correct. You could solve this equation, but you could solve this equation, right? Like, I was trying to save us time, but maybe I should just show you. Like, think about this one. If we had this x to the fifth plus 3x cubed minus 4x minus 8 equals minus 8, first step, add 8 to both sides, right? Just to take care of those. So we now have x to the fifth plus 3x cubed minus 4x equals 0. Then you can factor. This is also factorable. It's a quadratic form, but it factors. So it becomes x squared plus 4 times x squared minus 1, which you could factor further. And I can tell you specifically that there are 3 values that make this true. 0, 1, and minus 1. X squared plus 4 never equals 0. So, Ayers, I think my point with this is, well, yeah, you can't just look at that equation and go, oh, it equals 1. But we know how to solve equations. It might require us to do a little bit of work, but think about what the other option is, right? There's either the solve this equation, or there's the solve that thing for y. Yeah, and that's kind of the point, is that you got to think like a mathematician. Mathematician goes, it's an equation I got to solve. I can do that. We don't, I mean, and this is the math mentality. We don't care that, yeah, it's going to require us to do all kinds of weird stuff along the way to solve it. It's, oh, it can be done. As opposed to looking at this one and going, nope, no. Like, not only do I not want to do that, I can't do that. We don't have a nice way of solving quintic polynomials, quintic equations. If this was just like a y squared, okay, yeah, we can do that. We can use the quadratic formula. We can go through the process. We can find it. But something like this is literally impossible to solve. So we turn it from something that's impossible to something that's possible, just going to require some work. So, but that is good. I did kind of skip over that. But you do have to have an equation. You are going to have to solve whatever this equation is, which can get gnarly depending upon what the situation is.
How would you know which x to use?
Okay, so in this situation, you wouldn't have three choices. Here's what happened. I gave you a bad function. I made this one up. I was like, this has got to be 1-to-1. It turns out it's not 1-to-1.
Oh, gotcha. Okay.
So that was on me. If it's an invertible function, it's 1-to-1, which means there has to be just one answer to what gives us -8. I actually gave you a function that has 3 answers to that, so this is very much not 1-to-1. But so in reality, Aaliyah, you wouldn't have options.
Okay, good. Thank you.
If this had been a proper function and not a Bruce trying to go on the fly thing, which never works, by the way, there wouldn't have been, oh, pick one of these. It would have been, no, it's this one. Right? There is this value. So anyway, does that make sense?
Yeah, thank you.
All right. Okay, so long story, very long story, very short, is that now we can find derivatives of inverses without actually finding the inverse functions. That's huge. That's absolutely huge. Because now what we can do is find, say, the derivative of inverse tangent, inverse sine, functions like that we have no clue what their derivatives might look like. So let's do that now. Let's go get a whole bunch of more derivatives or a whole bunch of other functions that are related to ones that we know. All right, and so I think specifically, let's do this. Let's find, if we've got y equals, let's go inverse tangent. What is the derivative of inverse tangent? Okay, so that's our goal. Our goal here is to figure out what is the derivative of inverse tangent. All right, so let's think about what we need to do. So we need to first basically find what value will give us inverse tangent of x. What value do we plug into tangent to get that? And then we have to plug that into the derivative of tangent. So let me over here kind of write it out like what we're used to. So we're starting with f of x equaling tangent. And we want to find the derivative of the inverse, but I want it as x. No, I don't want to write it like that. Let me write it as f inverse of y. Because if we think about this as tangent, this is y equals tangent of x. Right? So y is what comes out. So this is basically, if we wanted to translate it to what we did before, that's what we're looking at. All right, so let's see if we can figure this out. So let's start with the derivative of tangent, right? If f of x is equal to tangent, what's the derivative of tangent? You guys remember?
Clear. Secant squared.
Okay, so it was secant squared. Good. All right, so what we know then is the derivative of inverse tangent it's going to equal 1 over secant squared, but evaluated at tangent of x. Okay, now this is probably where you go, whoa, whoa, whoa. I was all about the 1 over secant squared. Why are we putting in tangent of x? Okay, well, remember the way I kind of had this written out. This is the f inverse of y. So the question is, what do we plug in to get y? Well, we plug in tangent of x. We plug in that original function. So this is the derivative of inverse tangent. We're going to simplify it a bit. And I'm also going to rewrite it in another way because I think writing it as I did is maybe a little bit more confusing. But we've got secant of tangent of x. So we're plugging tangent into the secant. And then we're squaring that because of the secant squared. All right, so we just found the derivative of inverse tangent. It's the secant of tangent of x squared. And I can tell you're not really satisfied. I mean, I don't see a single one of your faces, but I can tell. You've got this like keen ability to, reach out in time and space and see into all of your rooms right now. And that sounded really creepy. I apologize. No, I can tell that the reason I say that is no one is ever satisfied with this. You're like, what? Seems like a bunch of nonsense. And what the hell is secant of tangent of x? Right. Well, check this out. We can actually simplify this. We can turn this into something we like a lot better using a little trig. So for those of you who had trig with me, which is not very many of you, but we did this kind of trick. Hopefully you saw this in trig. When you have composition of trig functions, oops, hold on a second. This is supposed to be tangent inverse of x, not tangent of x. I apologize, tangent inverse should be what's in there. But when you have composition of these trig functions, you can always simplify them if you just do a little right triangle magic. All right, and so I want you to think about inverse tangent for a second. Inverse tangent of x is an angle. This is an angle such that the tangent of that angle is equal to x. That's literally what inverse trig functions do. So if we've got this guy theta, think about getting a tangent of x. Tangent is opposite over adjacent. So if we think of this as, say, x over 1, the two sides of this right triangle that we know would be the vertical one is x and the horizontal one is 1. And if we know both of those, we can actually get the third side using the Pythagorean theorem. So that side's going to be the square root of x squared plus 1. Good old a squared plus b squared equals c squared. Okay, so now what we can do is we can figure out the secant of theta. And the reason I want secant of theta is because I was doing secant of inverse tangent. Well, secant is 1 over cosine. So that's hypotenuse over adjacent. So that's the square root of x squared plus 1 over 1. So if we go back to this original derivative, one over the secant of inverse tangent squared is the same as 1 over the square root of x squared plus 1 squared. And now that square root and that square cancel. And we get 1 over x squared plus 1. And that's what you want to remember as the derivative of inverse tangent. So inverse tangent, its derivative is 1 over x squared plus 1. Let me put a little box around that. Because now we're done. Okay, so turns out it's actually a pretty simple derivative. However, it takes a lot to get there. So let's just kind of remind ourselves what we did. We started by thinking about the original function tangent. We took its derivative, secant squared. Then we took the reciprocal of it, 1 over secant squared, and we put in the inverse tangent. We put in the inverse tangent because that's what we started with. Then we went back to trig and pulled some trig shenanigans to get rid of that composition, but it ended up getting us this nice little neat 1 over x squared plus 1. Okay, I know you're not impressed. I know you're not impressed at all. But to the mathematician, this is like, oh, hell yeah, check this out. We just got the derivative of the inverse tangent without really using inverse tangent. We were able to skirt around that thing the entire time. I mean, it showed up momentarily, but then we were able to just get away from it. So we found the derivative of inverse tangent without actually using inverse tangent. What the? Yeah, right. I mean, that's like the ultimate in math shenanigans. Like, it's just a huge trick, but yeah, we're able to find it. Okay, so I want to do another one. We're going to do one of the other. There are 5 more inverse trig functions, right? You got inverse sine, cosine, cotangent, secant, and cosecant. I'm not going to do all of them. I'm only going to do one more because they all follow the same kind of process. You can look in the book. There's a list that's got all of them. But I want to go ahead and show you one more, just so you can kind of see how this process flows and get a little bit better feel for this triangle business. All right. And in fact, I'll let you guys pick. Which of the other 5 do you want to see? First one I hear, or first one in the chat box gets it. All right. So Susanna is evidently a glutton for punishment because she requested cosecant. Usually people just pick sine, but we'll go cosecant. That's cool. All right, so we've got tangent, inverse tangent is 1 over x squared plus 1. All right, so let's try another one. Let's look at inverse cosecant. So we're going to have y equals cosecant inverse of x. And so the question is, what does y prime equal? So we'll leave a spot for it, but we're going to approach it the same kind of way. Let's start with cosecant. So if we've got f of x is cosecant of x, what's f prime? What's the derivative of cosecant? And this is when the rest of you are going to get mad at Susanna for picking cosecant.
Cosecant x times cotangent x.
Okay, so cosecant cotangent, that's very close. There's one other thing we need in there, Mariola. And you may have said it, I just didn't hear it. It's actually a negative cosecant cotangent. But that's the derivative of cosecant. So negative cosecant cotangent. Okay, so then we know that the derivative of the inverse is going to be 1 over minus cosecant of cosecant inverse of x times cotangent of cosecant inverse of x. So we just went 1 over, right? 1 over what we just found. But instead of x, I'm going to plug in the inverse function, cosecant inverse. Right? Go back and you look at what we developed, the very first rule for the inverse. It was always 1 over f prime of f inverse. Right? Okay, so now, now we get to evaluate those two things. So we've got two compositions. We've got cosecant of cosecant inverse and cotangent of cosecant inverse. So we're going to go to the right triangle and we're going to see if we can simplify that. Okay, so this is all coming from cosecant of inverse of x. So think of that as an angle. Again, this is an angle such that the cosecant of it equals x. So this is our theta. Let's think about cosecant. Cosecant is 1 over sine. Sine is opposite over hypotenuse. So this is hypotenuse over opposite. So in our picture, these will be x and 1. So the long side is x and the vertical side is 1. Okay, so far so good. Now we need to get this third side using the Pythagorean theorem. It's going to turn out to be the square root of x squared minus 1. Let me show you how I got that, just because I want to make it perfectly clear. All right, go to your Pythagorean theorem. A squared plus b squared equals c squared. So we put in the values that we know, the 1 and the x. So we get a squared plus 1 equals x squared. If I solve that for for a, I get the square root of x squared minus 1. Okay, so that's where that came from. Just Pythagorean theorem. But now I'm ready to actually evaluate those two compositions. Okay, so first things first, I'm going to put that negative just out front because I find that a little bit easier for me. So it's going to be negative 1 over. So let's start with the cosecant of the inverse cosecant. That one actually we shouldn't have to do anything for. Because what happens when we compose cosecant and cosecant inverse?
Cancel out.
They cancel each other out and we're left with just x. Okay, so there's going to be an x times. But now we need cotangent. All right, so cotangent. What's the cotangent of theta here?
1 over tan.
So it's 1 over the tangent. So tangent is opposite over adjacent. So cotangent is going to be adjacent over the opposite, which is the square root of x squared minus 1 over 1. Well, of course, dividing by 1 just leaves us the square root of x squared minus 1. So that's going to go in here. And so there is the derivative of inverse cosecant. So let me write it back up here because I notice it's in the glare a little bit. I apologize. 1 over x times the square root of x squared minus 1. So kind of crazy. we never actually did anything with inverse cosecant. We're able to just kind of run around it. Now, I do have to mention one thing, because this is now like math lawyer. Yeah, you know those lawyers that speak on commercials that are always like talking really fast with all the disclaimers? Well, there's a math lawyer. The math lawyer has to jump in here for a second and says, okay, but in order for this to actually work, one thing that we have to take into account, and it's okay that you didn't see this, but we need to put it in here. We need to put in absolute values around the x. This is a little quirky thing that has to do with cosecant and how cosecant is actually related to things depending on what quadrant we're in. So this is one of those I want you just to smile and nod. Sure, Bruce. Okay. Just put absolute values around that x. Okay. But there is the derivative of inverse cosecant using this fact of how inverses are related to each other. Whew. Okay, so there's inverse cosecant. So we can do the same thing for inverse sine, inverse cosine, inverse cotangent, inverse secant, right? We can list them all out. And they are in the book, all right? I know somewhere in this section, I want to say we're in section 3.5, maybe 6, I don't know. Somewhere in there, in this bit about inverse functions, you'll see the list of all of them. But really, I want to point out just a couple of them. And these are the ones that are going to matter later. Okay, so later on, these are the biggies. So let me go ahead and make you a little list of the ones that I want you to really key in on, as these are the important ones. Okay, so let me just make a list here. We got f of x, and then we'll have f prime of x. Okay, so the first one that's supremely important is actually the first one that we did. I always do that one first because it's super important. So inverse tangent, we saw that the derivative of inverse tangent was 1 over x squared plus 1. So that's the first one that's really kind of important. Okay, inverse sine, another biggie for later, but if we had gone through the process of finding the inverse sine, you would have seen that it was 1 over the square root of 1 minus x squared. Oh, by the way, you're going to see lots of 1 plus x squared, 1 minus x squared with these because of the Pythagorean theorem, right? Depending on how the 1's and x's all play out, you're either going to be adding 1 and x squared or you're going to be subtracting 1 and x squared. So those show up a lot in all of these forms. So if you go and you look at that list of all 6 trig, inverse trig functions, you'll see that. Okay, so inverse sine is 1 over the square root of 1 minus x squared. And I just realized I totally wrote that right in the middle of the glare on the screen. Sorry about that. Here's a little funky thing. Let me just aside. So you guys see this, the glare from the sun outside my window, right? When I look at the whiteboard, they're at completely different places because the angle from my eye is different than the angle from the camera. So I'm like, oh, I'm totally missing the glare. And then I look up here and I'm like, shit, it's right in the glare. So let me drop that down. I think it's better. So it was 1 over the square root of 1 minus x squared. Yeah, that's better. Okay, so there's another one of the biggies. So inverse tangent and inverse sine are the big ones. And then the other one that's like sometimes useful is secant inverse. And it actually looks a lot like what we just found for cosecant inverse. except it's positive and not negative. All right, so these are considered the big three when it comes to the inverse trig functions and their derivatives. But here's what's kind of cool is that the other ones, the co-functions, are virtually identical, just with sign differences, plus or minus sign differences, which shouldn't surprise you at all. Because we saw that the derivatives of the co-functions were the same, just with signs, plus or minus signs. And so since inverse derivatives are related to the original function derivatives, it shouldn't be a surprise that really it's just a plus or minus sign issue. All right, well, anyway, so inverse trig functions, you can actually find all 6 if you are so inclined using the same kind of trick. All right, I think I'm going to stop for today. I know we actually technically have a little more time, but we don't really have enough time to get into what I want to get doing next. So we're going to leave this for Friday. And Friday, we're going to keep playing with this idea of differentiating both sides and what we can do with that. And what's going to be kind of fun on Friday is you're going to see that we don't actually need a function to differentiate anymore. You can have think about like a circle. You can get an equation for a circle that's not a function, right? It doesn't pass the vertical line test. And yet we can still find slopes of tangent lines to a circle without actually making a function. So we'll see how we attack that. I know that we're scheduled for a quiz on Friday. We're not doing a quiz on Friday. Okay, so no quiz this Friday. Happy early Thanksgiving, I guess. No, early Halloween present. No quiz on Friday. So I'll make sure to put out a message in Canvas just to let everybody know. So that means we're going to start class at the usual time on Friday. Okay, we're going to meet at 8:30 like normal since you're not doing a quiz. All right. So other than that, I don't have anything to share. Anything else from you guys? Nope. Okay, well then you guys have a great couple days and I will see you all on Friday.
See you on Friday.